Hi everyone, my name is John Abdulmalik and I'm here to talk about the internals of Chrome. A quick introduction, I've been working on Chrome for um, getting close to 15 years now, mostly working on architecture related projects. Before I start, I'll remind you about Slido. There's a QR link in the top right, I believe. So please ask your questions there throughout the talk so that kind of when I'm done, we can go through them. So I'm going to start by describing how Chrome's unique architecture was built to support our core principles, the four S's of speed, security, stability, and simplicity. I'm sure you've heard about these already today, and you're going to hear about them again. And if it feels repetitive, it's because these are central to everything that we do. As you start making changes to Chrome, whatever function you're working on, these are the things you're going to keep in mind to make sure that Chrome is always the best browser that it could be. Um, I'm going to talk about also how we've improved architecture since launch. My motivation here is really when you look at the Chrome code today, you're going to find a lot of necessary complexity. And so if I was starting on it today, it would be a bit daunting to try to understand why everything is kind of the way it is, right? Or why is there so much complexity? So I hope to kind of explain that how it's evolved to get to the current state and why the reasons that it got to where it is today, and kind of hopefully that makes you understand why the things are the way they are, and kind of makes more sense. So first, though, I'm going to start about how I'll talk about how browsers looked like before Chrome. Everything ran in one process, and many were in the same thread. So this includes things like the rendering engine, the user interface, networking, storage, image decoding, third-party plugins. This is not optimal for a few reasons. A crash would take down the whole browser. So if you're typing like a long email and it crashed, even if a different tab crashed, then you would lose that data. Also, a bug could lead to code execution in the system, and which is bad for your security. But to be fair, this is how most apps were written, 20 or 30 years ago on desktop. And it's also not that big of a problem, right? A long time ago, you didn't have that many tabs. Also, you didn't have that much, information on the web to steal, right? I mean, maybe in the beginning there was email, but there wasn't even banking or documents or passwords. So there wasn't as much of an incentive for attackers to try to kind of exploit the bugs in your browser. So now I'm going to talk about what Chrome's architecture looked like when we launched in 2008. So as you can see, this is pretty different from before. There are multiple processes, each are denoted by a square, and they talk to each other over inter-process communication, which is a dotted line. I'm going to talk about that next. We also moved the code which we control, we have full control over the code, and which runs the untrusted content from the web into a fully sandboxed process, and that's denoted by the red border. As you can see, there are multiple renderer processes, roughly once per tab, and there were plugins which weren't under our control. We didn't control that source code, so they ran in a separate process that's unsandboxed. Here's a different way to look at it. It can show you which process draws which part of the browser. So you can see the user interface is drawn by the browser process, and the HTML, like the text on the page, is drawn by the renderer process. And then, plugins, this is back in the day when you needed a third-party plugin to show videos, were rendered by the plugin process. So why did we go through, the complexity and all the hard work of splitting the code into multiple processes? I mean, the main reason really is you just can't write perfect code. There's always going to be bugs that creep in, right? When you have millions and millions of lines of code. And so untrusted web content, right? Data that comes from potentially untrusted servers can be used to exploit these bugs. And so we don't want that to be able to be possible, of course. Also, sometimes it could be misbehaving, miswritten JavaScript that then causes a busy loop and a lot of CPU consumption. And you don't want it to be able to disrupt your access to other tabs or even the ability to interact with the browser UI. And then lastly, a crash shouldn't take down all the browser and all the other tabs because that is very disruptive. I mentioned earlier that processes talk to each other over inter-process communication. This is basically message passing between processes. And if you have large data, you use shared memory. It's almost always asynchronous for performance reasons. So while synchronous IPC is possible, it's heavily discouraged. And usually we use it when there are old web APIs that kind of required synchronous access, and just because that was before the days of multi-process. The thing to keep in mind with IPCs is it's usually between processes of different privileges. So that's why every time you'll change like an IPC, you're going to have to go through a security reviewer, and these are kind of security engineers who are much better trained than the average engineer to kind of spot where there could be security bugs. I mentioned also sandboxing earlier, and since untrusted data can be used to exploit bugs in the code that we write and on arbitrary code, we need to protect against that. And especially as web pages move from simple, pages that you display to running full-featured web apps, there's a lot more code to exploit. So we wanted to run the untrusted code in a lockdown process where it doesn't have access to things like the file system and to be able to interact with other applications running on your machine and so on. The exact mechanism to do this, of course, is very system dependent. So every platform has its own sandboxing code. And there are multiple different levels of sandboxing. So some processes could be sandboxed much more fully than others, depending on whether they have to run, drivers or other code in there. Now, the main kind of child process type that we have is a render, and this is where data from the web is handled. So things like parsing the HTML, doing the layout, executing JavaScript, decoding images, and this one is completely sandboxed, so it has absolutely no access to your system. And this prevents, bad code from being able to access your data or install long-lived malware. A plugin process is what we used to run things like Flash and Reader and so on. And it was based on NPAPI programming language, which is over 25 years at this point, or the NPAPI interfaces. And since we had to work with existing plugins when we launched, these plugins assumed full access to the system, so they had to run fully unsandboxed. The browser process, lastly, is a central coordinator. It owns a browser state, things like your profile data. It draws a user interface and makes a networking requests. And all the code that's basically not page-specific lived here. It's much more privileged than the renderer, so we have to be careful every time the renderer talks to it to make sure that an exploited renderer isn't trying to trick it. And generally, thread-wise, in every child process, there's usually a main thread, and then there's a thread that's doing the IPC. There are many more threads than that, especially as time goes on. There's things in the browser, many threads for doing storage access, and also in the browser process, the IPC thread also was responsible for doing non-blocking I/O, like talking to the network. So now let's move forward a decade later to see what Chrome looked like around 2015. Now, I'm not stopping at where we're currently at. I'm kind of doing like a stopover point just to show the progression of the architecture. So this is what Chrome looked like then. We gained a bunch of new process types. There's GPU process, utility process. We forked WebKit into Blink, and we replaced NPAPI with a new plugin API that's sandboxed. I'm going to talk about each of these in the next slides. So the first one is a GPU process. We noticed that machines with more powerful GPUs were becoming widespread, and what platform features like WebGL meant that we would have to make expensive GPU readbacks to render a page. So this was a very large project to offload the compositing and the scrolling to the GPU. And we run it in a separate process because the GPU drivers could have bugs, so we didn't want a bug in these drivers to be able to exploit your machine. And the end goal of this is improves performance and power usage. A utility process is something also that we gained. And the reason is, as the browser gained more features, there were new classes of untrusted data that just didn't belong to a specific page, where it could run in that page's render process. Things like installing an extension or processing JSON that came from the server. So the utility process is used to run this short-lived kind of computation in a fully sandboxed process and get the data back. And when we launched, we didn't have extensions, and that was kind of a design decision that we made so that we don't kind of take forever to launch a browser. But of course, that was always in our roadmap. But at the same time, when we added extensions, that still had to work well with our 4S's. So we didn't want badly written extensions to affect pages, right, to slow them down. We also wanted extensions to have limited access to your state, and so that doesn't have full access to, for example, your cookies. We also wanted extensions to be able to be installed and uninstalled with our browser restart. So kind of that's these are some of the reasons why they wanted a separate process. And then Pepper plugins. Well, the renderer was sandboxed when we launched, right? But NP API was a convenient source of cross-browser exploits. So you'd write one bug, you'd find one bug in one plugin, and it would exploit all your browsers. So it was kind of very easy for exploit writers. So we spent a few years making a new plugin API that supports sandboxing. And we ported Flash, working along with Adobe, to this new API. And we also wrote a new PDF plugin based on code we licensed, which is PDF. So then after kind of all these new processes, another massive kind of architectural change was this thing called Chrome content split. For code health reasons, we wanted to split the product, which is Chrome, from the platform. What we consider the platform is a sandbox multi-process browser. So we split source Chrome into source Chrome and source content. And source Chrome is where the UI and browser features, things like bookmarks, password manager, autofill stayed. And then content was where we removed everything related to multi-process and sandboxing and the web platform. And then even though we did this for code health reasons, the interesting thing is this allowed new products to be built on top of our platform. Things like Chromecast and Electron and Home and so on. And then another big architectural change was componentization. And this was kind of a side effect of iOS enforcing that every browser had to use the Safari engine. And so we couldn't use Blink. So this meant that for browser features that we want to share, things like our password manager or autofill or sync, we had to separate that code into two pieces. One that's generic and independent of the rendering engine used. And then the other piece, where either it was content, right, for things that were at Blink, or it was, iOS specific code. Site isolation is also another massive effort that we did. And the reason there is as more of our data moved online, guarding against exploits on a page wasn't enough. You had to guard against exploits in one page, kind of interacting with other parts of the page. So for example, if you're evil.com and you can get an iframe from good.com menu, or you could somehow trick the good.com into embedding an iframe from you through ads or some other mechanism, then you can have code running in the same render process, and you can steal the other site's cookies and so on. So this large project allowed us to split different iframes on a page into different processes and use multiple processes per page. This is like the biggest security and re-architecture improvement since launch. It allowed us to mitigate things like Spectre attacks. And then Mojo is a term you're going to hear a lot about. And it was our new IPC mechanism built on 10 plus years of lessons we've learned and solve limitations. Some of the issues we had with our old template-based IPC system was it was very hard to send platform handles. Like you had to know which process you're going to, and is that process sandbox or unsandbox, and the code would be different if the other side, was code that was running in a different process or in the browser process, which, depending on the platform and system memory, for example, might move. Also, we couldn't send IPCs directly from the Blink rendering code, so we had to go through content, and this added extra layers and conversions, which was just kind of busy work and also, not good for performance. So kind of Mojo hides all this, and kind of you can send platform handles and they will get brokered transparently. And it allows generation of bindings for different languages. So for example, you can have a binding that's written for JavaScript code or Java code. And you can even have different bindings for the same language. So, Blink has its own string type. So we have Blink bindings that use WTF string, while, the rest of the code uses STL strings. There's only a small number of Mojo primitives. There's message pipes, which are bidirectional communication channels. And, there's two for each interface, basically, one for the caller and one for the callee. They're pretty cheap, so they can be considered basically free. There's no OS resource per message pipe, no separate buffers, etc. Usually, you don't use message buffers directly or message pipes directly. You use them through kind of these bindings, which are higher level mechanisms on top of them. And then there are shared buffers, which are just shared memory. And there are data pipes, which standardize this common ad hoc implementation that we had all over the code before, which is basically shared memory along with a signaling mechanism. And all these primitives can be passed around threads on processes. So you could use them on one thread and then pass it to a different thread or a different process. And you can also even just use an interface a bit, and then once you're done, pass it somewhere else, and then the other place can start using it. So you probably know this also looks a lot like message passing or capability passing. As you pass these interface objects around, it's almost like you're giving new privileges to another process. Now, how does current Chrome look like from all these improvements I've described before? So a large project was something called Servicification. And the motivation here is, as Chrome expanded across many more platforms that we never foresaw in the beginning, we encountered limitations in our architecture. So Servicification was a project to move code to a microservice architecture. And services are well-defined, so they have a clear API. They're reusable, so there's kind of fewer ways of doing the same thing. You call feature the same way, independent of which process you're in, which thread you're in, or which language you're in. And services are decoupled from each other, so they have kind of very limited dependencies. And we can maybe run some of these services alone without the whole browser. And the system is all layered, so services can depend on each other. For example, LevelDB can be built on top of file system. So what are the benefits? Again, I'm going to talk about the 4 S's. So one of the benefits is reduced conversions as we cross the code or process boundaries. Different processes can use the same interface, or before they would have different interfaces to get to the browser, and then the browser would use a real interface. You have the flexibility to run subsystems closer together. So for example, you have the ability to take some service and run it maybe in multiple processes at the same time that have different privileges. You also have more sandboxing. If you move things like networking to a separate process, you can then sandbox that process, and now all this parsing, and all this protocol parsing can be sandboxed. And you have better stability, because as you move code out of the browser process, you move crashes from the browser, which is kind of unrecoverable, to a child process, which is recoverable. And then simplicity, I'm going to override. Usually for S's, simplicity means user interface simplicity, but here I'm going to use it to mean code simplicity. So this is easier for developers because we have consistent APIs to subsystems, and instead of each kind of framework defining its own API. There's there's fewer duplicate APIs. So what does it look like? So here's the kind of diagram that shows, as you can see, there's a lot more processes. So for example, you can move the device access to a separate process, and that improves stability a lot, because often drivers are a source of crashes. You can also move storage to a fully sandboxed process, which we're doing now. The networking, which we moved a few years ago, is also running in its own process, and it's now being sandboxed. And now, one thing to be very clear is, just because something is a service, it doesn't mean it has to run in a separate process. It just means that you could run it in a separate process. So for example, let's say you have a low memory device, like a phone with like 2 gigabytes memory. It's trivial to just run services in the browser process, which, of course, removes the per process overhead. And so before, where this was a lot of work to handle, different paths for where code runs, now it's one if statement where you can control where a service runs. And then even cooler example of this is you could run a subset of the browser without all the code using this model. So for example, let's say you want to do some background work on Android when the browser is not running. So you could just load up only the networking and storage services. And we do this today. Now I'm going to progress to just a quick overview of the directories that hold the kind of code that we've talked about before. So there's base, which is kind of like that lowest level code that has hosting file access string information. There's a Chrome directory, which is desktop and Android, but not iOS. And there's source components, which is where we've componentized features that we share between the desktop and iOS. And then there's content, which is our multi-process sandbox platform. And iOS is where our browser on iOS lives. Net is kind of all the networking code that we have. Services is where our microservices live. Third-party Blink is our rendering engine. UI is a lot of our helpers for drawing user interfaces on different platforms. And V8 is our JavaScript engine. So I will take it to Q&A now. Let me refresh the page. Aha, okay. Who's going to be the first to type? Any questions? Okay. Usually in the live sessions, a lot of questions. Okay. Well, my email was in the first slide. So if you think of any questions later, please feel free to contact me. I'm happy to kind of answer any questions. And welcome to Chrome. Thank you.